Okay, ready? Shall we go? Yeah, okay. So today our mathematician spotlight is Henri Sagermann. He's an assistant professor at Oklahoma State University. This is what he looks like. He's originally from England. And he studies three manifolds, triangulations, and hyperbolic geometry. One of the really cool things that he does, you can come in if you want. Feel free to come in. I'm speaking to you guys in the hallway, okay, is that he does mathematical visualization, 3D printing, and virtual reality. So he studies hyperbolic geometry, which is space that's curved in a different way than what we're used to. So he makes these things where you can put on 3D glasses, so you can put on glasses and like move around, virtual reality, and you see what it's like to be in hyperbolic space. So that's pretty cool. That technology is pretty new, like in the sense that people are working out how to make it happen. And one of the really neat things he does is he designs 3D printed objects to do mathematical things. You can see two of them in this picture. And I think that they blend math and art. So I'll just show you a short video, which I just had running at the beginning of this, this thing, and I'll let him explain it to you.
Hi, my name is Henri Sagermann. This is stereographic projection, or rather this is a sculpture that illustrates stereographic projection. So stereographic projection is a map from the sphere to the plane. And the way that it works is you look at the north pole of the sphere, and you draw straight lines from the north pole down to the plane. Each such line hits the sphere once and hits the plane once. And so the map from the sphere to the plane is where does the line hit the sphere, that maps to where the line hits the plane. And why are we sitting in the dark? Well, straight lines are pretty well approximated by light rays. And so this is the light on my cell phone, which is a pretty good approximation to a point light source. And if you arrange the light at the North Pole, then the light rays effectively do stereographic projection. And these curves on the sphere are mapped to the straight line grid on the plane. This is stereographic projection.
Pretty neat, huh? So yeah, he makes these 3D sculptures, and he sells them, and then he also lets you buy them so you can print them out yourself if you like. Okay, so I'll leave this up because we're going to do something with this surface. Okay, so last time we talked about how to parameterize a surface, how to describe a surface parametrically, and that. Okay, we talked about that. And the other thing we talked about that is how to find a normal vector to the surface, because often we want a normal vector. I talked briefly about how you might want a normal vector, because later we'll figure out how much a flow flows through our surface, so that'll be in the direction of the normal vector. And today we'll just use a normal vector to find a tangent plane, which is something that we did with non-parametrically defined surfaces a month or two ago. So as you know, our plan for the last month or so of the semester is to learn to integrate scalar and vector valued functions over curves and surfaces. And we've done curves. You can integrate scalar valued functions over curves, and you can do vector line integrals over curves. So that part is done. And today we'll be learning to integrate scalar valued functions over surfaces. So that will start today. Okay. So let's start by just finding a tangent plane to a surface. So for example, so I won't make fun of anyone that's coughing, but if you're actually sick, you should stay home. Because we don't want everyone else to get sick, and we want you to make sure that you're resting and becoming well. That's the most important thing. Okay, so find a tangent plane to, as you guys know, I pushed myself too hard and then I ended up in the hospital. So don't let this happen to you. So find a tangent plane to my favorite surface, which is currently on the screen, and whose parameterization is x of r comma theta is r cos theta r sine theta. Okay, that just gives you an x and y place in the plane, and then cosine of r. So that tells you that however far out you are, that's how high up you go. So the further out you go, it sort of like undulates. And you can see on this picture on the screen what the surface looks like. So I like this because I feel like it's like you drop a bit of water into a pond and then it radiates outward. In a real pond, the ripples would get smaller as you go out, and you can certainly do that too as a surface. But I didn't choose to do that today. Cool, right? Cool surface? Very cool surface. Okay, so let's find a tangent plane to this surface at the point 1, 0, cosine of 1. So this is a point described with this x, y, and z coordinates. So, but here we're parameterizing in terms of r and theta, so we should figure out what r and theta are. So it's at r equals 1 and theta equals 0. So that's what we want. So let's explore how to do this. What we figured out the last time was that a good way to do it, well, to find a tangent plane, you need two vectors that are in the surface. Well, you don't need it, but that's some way to do it. You take two vectors that are in the surface, and you take their cross product, and that gives you a normal vector that's perpendicular to both. So that's our goal, our scheme, is that we're going to find these two vectors that are in the surface. This little plane that I've drawn is just a little piece of a curved surface. One of them is going to be a vector in the r direction, and the other one is going to be a vector in the theta direction. So let's do that. So the first one, we could call it r curves. So an r curve on the surface means you hold theta constant and you vary r. So let's see what sort of thing these would look like. So for example, if we let theta equal 0, then plug into here theta equals 0. So cosine of 0 is 1, so this is r. Sine of 0 is 0, so this is 0. And there's no theta here, so this is just cosine of r. So it tells you that if theta equals 0, okay, that's if you're on the x-axis, you just go r 0 cosine of r. So that's very much like going x 0 cosine of x. You just do x in the x direction, and your z value goes like cosine of x. And then similarly, what if theta equals pi over 2? Then if you plug this in, well, cosine of pi over 2 is 0. Sine of pi over 2 is 1, so we get r. And again, cosine of r. So this is just like a cosine wave in the y direction. So I'll plot these on here. Let's see. So this one, if we do, you can see I have put in u 0 cosine of u. Here u is just r. And so this curve undulates out along the x-axis. Can you kind of see this curve? So when you graph anything on a computer, it's an approximation. So the surface, actually, each of these little colored panes, it's just drawing them as a flat plane. And this curve, it should be sitting exactly in the surface. But sometimes it looks like it's above the surface, and sometimes it looks like it's below the surface. And that's just because of the computer's approximation. And then if I do the one for the y direction, theta equals pi over 2, we get a curve going away from us. Can you see it? This is the x direction one, and then this is the y direction one. So these are the r curves. This is what happens if you fix a theta and you vary r. You just undulate away from the origin in a cosine graph. So those are the r curves. I could have drawn many of them going around. Okay, let's think about the theta curves. So that would mean hold r constant and vary theta. So we go out a distance r and we vary theta. It should be some sort of circles. So let's think about theta curves. So that's you hold r constant and vary theta. So for instance, let's just do two examples. If r equals 1, then we get cos theta, sine theta, and then cosine of 1. Okay, so cos theta, sine theta, that's a unit circle. And it tells you it's just a unit circle whose z value is cosine of 1, so up a distance of 1. And how about if r is 10? Then we just get 10 cos theta, 10 sine theta, cos 10. So this is a circle of radius 10, bigger circle, up or down a distance of cosine of 10. I'm not sure if cosine of 10 is positive or negative, but that's what its z value is. So let's graph those. So I put those in. Cos t sine t cosine of 1. Can you even see it there? There it is. Hello. So it's this little circle here. So again, the circle is supposed to be sitting right on the surface, but because the computer is doing an approximation, it looks like it's sitting above the surface. But that's because it's making this top bit into a cone, basically, so it's not exactly right. But this is supposed to be sitting on the surface, and then if we do the one with radius 10, it's something else. We're going to have to zoom out to see it. Do you see it? Can you spot it anywhere? No, we figured this out. It's actually underneath. There it is. Okay, so because of the approximation, it actually put the whole thing underneath the surface. So, okay, we couldn't see that one, but luckily this is actually the one we care about. Now let's plot the point that we care about. We are supposed to find the tangent plane at 1, 0, cosine of 1. So that's this point right there. So that's going to be our dream, is to find the tangent plane at this equation, so at this point. So it'll look something like this. Okay, let's do it. Okay, to find a normal vector to the surface, I'll call it surf, the surface, find two vectors tangent to the surface, and then take their cross product. So that's the idea. That's exactly this picture that we had here. We have two vectors that are in the surface. We take the cross product. We get something perpendicular to both. So to find vectors tangent to the surface, we'll do the vector in the r direction and the vector in the theta direction. So let's do xr and x theta. So xr and x theta. And to help with that, I'll just write down x r theta again. So that's right here. It's r cos theta, r sine theta, cos r. Okay, so we take the partial derivative of this thing with respect to r, and we get cos theta, sine theta, negative sine r. Okay, and then we take the derivative with respect to theta, and we get negative r sine theta, r cos theta, 0. Okay, so for any possible point r comma theta that we wanted, these would give us the vectors in the r and theta directions. We care about the point 1, 0 cosine 1, so we care about when r equals 1 and theta equals pi over, no, theta equals 0, I believe. So in this case, xr is, let's see, if theta equals 0, this is 1, 0, negative sine of 1. And then x theta, these are both vectors, is 0, r cos theta, 1, 0. Okay, so these are the two vectors in the directions of xr and x theta. In our picture, the xr vector, which was 1, 0, negative sine of 1, is this guy here. And that looks pretty reasonable. It does look like the z is going down, negative sine of 1, so that's good. And then the other one, it's 0, 1, 0, so it tells you that it's going purely in the y direction, and that also seems reasonable. Z isn't changing at all, for instance. So it seems like we probably got it right. Okay. So now that we have these two vectors, these are both tangent to the surface. So to find a normal vector to the surface, we'll do r cross x theta. It doesn't matter which order you do it. If you did it the other order, you would get a normal vector just be pointing the opposite direction. So let's do r cross x theta. So that's I, j, k, and then we put these vectors in. So 1, 0, negative sine of 1, 0, 1, 0. Okay, let's do this. So it's 0 minus negative sine of 1. I think that's positive sine of 1. And then 0 minus 0 is 0. And then 1 minus 0 is 1. Okay, so allegedly this is a normal vector to the curve. So let's try it. So one way to test out if it's right is to write a parametric equation where you start at the point 1, 0, So I'll just show you. So if I started at the point 1, 0, cosine of 1, which is our blue point that we have put, and then we go in direction sine 1, 0, 1. So we multiply those by t. So that gives us this line coming out. I hope that you can see it. You see it there coming out? Does it look perpendicular? Looks vaguely perpendicular. Maybe we should look at it from the side. I think it looks pretty good. It looks pretty perpendicular. Sorry that the lines are so thin. I can thicken them, but then every time you move it, it goes back to thin, so it's not worth thickening them. Yeah, okay. So that's it. Now we're ready. So to write the equation of a tangent plane, so to write, in fact, the equation of a plane, you need a point on the plane. So for us, that's the point we were given that where we wanted to find the tangent plane, 1, 0, cosine of 1. And we need a normal vector to the plane. And we just figured that out. That's sine 1, 0, 1. So those are the two things that we need. And now we can find a plane equation. So we derived a formula for how to find a plane equation with these two things. But I want to remind you why it works. So here's the idea. Here's the plane. And you know you have a point on the plane. The point that you have on the plane is 1, 0, cosine of 1. That's the point. And then you also know that you have a normal vector to the plane. Here it is. Your normal vector is sine 1, 0, 1. And you want to figure out how to describe this plane. And the brilliant idea is to realize that, well, okay, you want to describe the plane, yes, but what you really want to describe is all the points on the plane. So if you want to describe all the points like x, y, z on the plane. And the idea is to realize that the vector between the point we know, 1, 0, cos 1, and any other point x, y, z is perpendicular to our normal vector. So so the normal vector is sine 1, 0, 1. That's our red vector. And when we take the dot product of this vector that's in the plane, that's x minus 1, y minus 0, z minus cos 1. Well, those two things are perpendicular, so we should get 0. So that's the idea. You put your normal vector, and then you find a vector in the plane using the point you have and any other point x, y, z on the plane. And those two things are perpendicular. So now let's just take this dot product. So this just says sine 1 times x minus 1 plus 0 times y minus 0 plus 1 times z minus cosine of 1 equals 0. And that's our plane equation. Done. And if you wanted to make it look more tidy, you could multiply out. So sine 1 times x minus sine 1, this part is 0, plus z minus cos 1 equals 0. Maybe it's nice to put all the variables on one side and all the constants on the other side. So sine 1 times x plus z equals sine 1 plus cosine 1. So there's an error on your sheet. It says sine 1 cos 1 minus sine 1 because I added incorrectly. But this is what it should be. Any of these are perfectly good as plane equations. And let's try it out. So when we type this in, put this into the thing. Boop. Hey! It looks pretty good. It looks like a tangent plane. So that's the idea. Yeah, questions or ideas? All right. So with parameterized surfaces, you'd be good. Okay. Now, let's see. I'm going to take off this tangent plane so we can see this surface in all its glory. And maybe I'll take off this line too. Okay. So check this out. Now, this surface is really cool. Do you guys remember, do you know what the word fascinator means as in terms of fashion? Fascinator. Anyway, okay, I think it would make a really great fascinator. So back when Prince William got married a bunch of years ago, the royal wedding was broadcast on TV, and everyone in America was like, what are those women, what do they have on their heads? Because they weren't all just wearing fancy hats. Some of them were wearing ridiculous things like attached to the side of their head. Does this ring a bell at all? No? Believe me, when British women get dressed up, they attach weird things to their heads called fascinators. This, I mean, it might make a great hat, but there's not much place for your head, so I think it would make a really great fascinator. But here's the thing, if I'm going to make this into a fascinator, I'm going to need to know how much fabric I need. You know? And if it's going to be a fancy thing, I probably don't want to overbuy my fabric. I just need to know exactly the amount that I want. So I might want to know the surface area of this surface, which is something that we can't do yet, right? Because it's not a sphere. It's not anything that you know how to find the surface area of. So we should figure out how to find the surface area of such a surface. So that's the next thing to do. OK, and we'll make it go away so that we can have more space for everything else in our lives. OK, so suppose you wanted to find the surface area of something. So surface area of, in particular, a parameterized surface. OK, so here's the idea. You have some surface, maybe it's that thing. In general, I'll just draw some sort of a lump. And this is a surface, so, those probably shouldn't cross. Let's keep them going. Nice, nice. And then we have some curves in the other direction. OK. So maybe these white ones are our S curves. I'll write S curves. And maybe these purple ones are our T curves. So the idea is, like, for the T curves, you're holding S constant and you're varying T, and you get different purple curves for the different values of S that you pick. Just like we had different R curves undulating out for different values of theta for the cool surface. OK. And we want to maybe know what is the surface area of this piece of the surface. So here's the tool that we'll use. So recall, if you would, maybe you won't, but I'll tell you. If you have two vectors, u and v, and you take their cross product, u cross v. OK, so their cross product gives you a vector that's perpendicular to both. We just used that. But how about their magnitude? The magnitude of the cross product. Like, who cares about the magnitude? It's just a direction that's perpendicular. Well, the magnitude has a meaning. It's the area of the parallelogram spanned by u and v. So that means, what that means is this parallelogram here. So the magnitude, that's what these bars mean, magnitude, gives you the area of the parallelogram spanned by these vectors. So we're going to use that to find the area of the little piece here spanned by our two vectors. So, suppose you care about the little piece of area that's here. Here's a vector. This one is like xs, the direction in the vector in the direction tangent to the s curve. And then there's also this vector here, xt, the vector tangent to the t curve here. So let's find this little area of this little parallelogram in here. And then we'll add them all up, and that'll give us the surface area of this little patch of the surface. That's the idea. So the idea is that in this same way, the magnitude of xs cross xt is the area of the parallelogram spanned by xs and xt. OK, but that's actually not so useful, because xs and xt, they're so big. Like, when you make them so big, they're not even touching the surface anymore. Like over here, our xr and x theta were 1, 0, negative sign of 1, 0, 1, 0. Those are like length 1 vectors. That's so big. That's not what we want. What we want is like a little tiny amount. So the trick is that instead of using xs, you use xs times some tiny little distance ds. So here, I don't know, maybe ds is like 1/3. because I'm using 1/3 of this vector, approximately. And then you also use xt times dt. So here, maybe dt is 1/4 approximately because I'm only using 1/4 of this vector. Of course, using 1/4 and 1/3, this already isn't a very good approximation. It's kind of like our picture of our surface on the computer, where the panes were so big that it made a difference and our curves didn't sit on the surface. So what you'd want is to take a tiny infinitesimal ds. So what we do is we'll add up the magnitude of this vector over the region of the ST plane that we're interested in when ds and dt are infinitesimal. And the last thing to say is that the cross product distributes over scalar multiplication, so we can just pull out this ds. It's just a constant. And in the same way, we can pull out this dt. So if this had been 1/4 and 1/3, like in the picture, we could just pull it out and say it's 1/12 times this cross product. So this is the double integral over the region in the ST plane that we care about of xs cross xt times ds dt. So this gives us the surface area of the surface area of the surface corresponding to the region D in the parameter space. ST space. Okay, so good, we should try it. Okay, and then what's happening? I should tell you what's actually happening here. So what I mean by parameter space is you have S and T space here, and then you have this little ds and this little dt. And let's see, if you fix S and vary T, you get T curves. So these would be the T curves. And if you fix T and vary S, you get this sort of thing. And so ds dt is a little area in parameter space. And then our parameterization takes us to the surface. Maybe I'll make these smaller so that they look better. It takes you to maybe this little box right there. And you want to know what the area expansion factor is. So actually this magnitude of xs cross xt is just a Jacobian expansion area expansion factor. So want xs cross xt, which is just the Jacobian area expansion factor. So we're just doing area expansion factor except on surfaces, and we'll see at the end that in the xy plane it just reduces to area expansion factor, but now we can apply it to surfaces. Questions or ideas? Yeah, all right. All right, so anytime you get a new formula or a new trick, the first thing to do is to apply it to something where you know the answer so you can check if it's right. So I think the first thing we should do is to find the area of a cone. So example, so find the area of a cone of radius r, let's use big R so we don't get confused, and height h. So here's a cone. Its height is h, its radius is r, and the part that I want to find the area of is just the slanty part. Please, not the flat top, just the slanty part, this part. So we want to find that. Okay, if we just did this, we'd get some number and we wouldn't know if it was right. So let's check it. So method 1, let's just use geometry. So an easy way to measure the area of a cone is to just slice it down the side and lay it flat, and then you'll get a sector. So if we cut this, we'll get some sector that looks like this, something like this. My circle got a little bigger on the right than it was on the left. It's not really a circle anymore. There, okay, great. So there we go. and find the area of this thing. So first we need the radius of this thing, which is just this diagonal length of the cone, what they call the slant height. So this slant height of the cone, using the Pythagorean theorem, you can figure out it's big R squared plus h squared. So this radius here is big R squared plus h squared. So the area is like the area of the entire disk of radius, that big thing, big R squared plus h squared, times the proportion that we have. So the area of a disk of this radius is pi times the radius squared. So pi times square root of r squared plus h squared squared times the proportion that we have. So you could say it's the angle that we have over 2 pi. That would work. Then we have to find the angle. That sounds like a mess. Or you could just use the proportion of the circumference that we have. So we could figure out what proportion of the circumference we have. So this length is the same. This is where it came from. It came from up here. So let's find its length. Up here, we can figure out that its length is 2 pi r, big R. So over here, once we've cut it out, its length is still 2 pi r. So this is 2 pi big R over the circumference of the whole thing, if we had the whole thing. So that would be 2 pi times, again, big R squared plus h squared. So this is the area of the whole disk times the proportion that we actually have. That should give us this yellow area. Let's cancel some things. 2 pi cancels with 2 pi. One of these square roots cancels with one of these square roots. And we get pi times big R times square root of r squared plus h squared. Okay, so there we have it, the area of a cone, just the outside of the cone. Okay, there's method 1. Let's try method 2, calculus. So method 2, parameterize the cone and use the surface area formula. Okay, method 2. So let's do it. So x of, probably r and theta would be good variables to use. Let's use them. So x of r and theta. So I just want a point in the xy plane. So r cos theta, r sine theta. And then I want to know how high I am in my z if I do this. So let's think about our favorite cone. The cone where if you go out a distance r, you go up a distance r. Like the cone z equals r. I think this cone was even on your exam. You've thought about it before. So if I went out a distance r, I'd go up a distance r to get onto the cone. So this would just be r. But that's not what I have here, because h might not be equal to big R. In fact, here it looks like h is bigger than big R. So I'd have to multiply by something. So it tells you that however far you go out in radius, you have to multiply by h over big R to see how much you go up in z. So this should be h over big R times r. So if you go out a distance little r, you go up a distance little r times this sort of stretching factor, big H, h over big R, to get you up to the cone. Okay, so there we have that. Now to do our surface area formula, we're going to need the cross product of the vectors in the r and the theta directions. So let's get the r and the theta vectors. So xr is cos theta, sine theta, h over r, big R, and x theta is negative r sine theta, r cos theta, 0. And we'll want to compute xr cross x theta. So set up I, j, k, and these two things. And when you do it, I'll just skip that step. We get r times square root of big R squared plus h squared over r. Is that right? Is that right? Okay. Okay, so if you do this, you get this number. Now this looks like a really complicated thing, but note that this r is a variable, but this whole thing is just constants, because big R and h are just constants. Okay, so to find the surface area, It says we should take the double integral over the region we're interested in of the magnitude of xr cross x theta dr d theta. Now, one thing that I forgot to do when I parameterized my surface was say which r's and thetas we cared about. So let's do that now. So to get this whole cone, I want theta, well, I want the whole cone, so I want theta from 0 to 2 pi. And I want r, well, from 0 for sure, out to all the r's until I get the whole cone. So it looks like I'm going to need r to go out to big R. So r goes from 0 out to big R. OK, and this is the domain in the r theta plane that we care about, that gives us our cone. So this is going to go from theta equals 0 to 2 pi, from r equals 0 to big R, of the magnitude of this thing. So that was little r times this constant, big R squared plus h squared over r times dr d theta. OK, and now we can just do it. So this thing is a constant. We can just pull it out all the way to the outside. So square root of r squared plus h squared over r. And then notice that our only function is r, and all of our variables are constant. Our bounds of integration are constants. So we can pull it out. This is the integral from theta equals 0 to 2 pi d theta times the integral from r equals 0 to big R, r dr. And we can just do them all separately. So we get this big constant on the front, square root of r squared plus h squared over big R, times the integral of d theta from 0 to 2 pi is just 2 pi. And the integral of r dr is r squared over 2. So we get big R squared over 2 minus 0. So let's see how it works. Let's see if we got what we wanted. This 2 cancels with this 2. One of these r's cancel with that r. And we get pi times r times the square root of big R squared plus h squared. Huh! Is it what we wanted? Hey! It's what we wanted. It's the same. So we're checking that these two things are the same because we computed this with geometry and we computed this with calculus, and they came out the same. Yay, so it seems to work. So we don't disbelieve it. It seems plausible. So the idea of what we did there was we parameterized our surface in terms of r and theta. We figured out which r's and thetas we needed to give us the whole cone. And then we just put it into the surface area equation. You want the size of the normal vector. So we took each vector and we took their cross product. We skipped that step of taking the cross product, but the answer, the magnitude of the cross product is this thing. And then we integrated that dr d theta. Yeah, questions or ideas? Okay. So one thing that I said is that this magnitude of this cross product is a Jacobian expansion factor. So you'll notice that when we computed it, we got r times this thing. So that's basically just like our r dr d theta. You see, if I put my hand over this, you get r dr d theta, which is our thing for polar coordinates. But then we had to multiply by this expansion factor because it wasn't just a disk in the plane. It was like a cone that was multiplied, like stretched out. Yeah. OK. Sort of like if you had a rubber cone that was nailed down at the center. Sorry, if you had a rubber disk, like a piece of a balloon that was rubber, and you put a nail at the center and nailed it down, and then you pulled it up, it would look like a cone. Surface area would get bigger, and that's what this is doing. OK, so so the last thing to do is to now start integrating functions. Yes, which I'm erasing now, but I said we were going to integrate scalar functions over surfaces, and indeed we are. So let's do scalar surface integrals. So you will remember probably that if you want to find the area of some region, you integrate the function 1. If you want to find the volume of some solid, you integrate the function 1. If you want to find the length of a curve, you integrate the function 1. And so similarly, if you want to find the area of a surface, you integrate over the part of the parameter plane that you're interested in, 1 ds. And this S is a big S. It's like a surface S. It's just like dA, like an area differential, but it just acknowledges the fact that it's not sitting in the plane, it's sitting in space. And the way that you do that, well, we just did that. It's the double integral over d of the magnitude of Sx cross xt ds dt. And you might wonder what on earth happened to the S, or what on earth happened to the 1, and the 1 is just in the front. And then this is the ds. So that's what we're integrating, 1 ds. So suppose that you are, you're creating your beautiful fascinator, and instead of just having just a piece of fabric to make it, to stick it onto your head, you wanted to have like a little bit of maybe gold leaf over there, and a little bit of silver stitching over there, and a little bit of pearls over there, so it doesn't cost the same amount everywhere. You want to know you have amount that it costs at each point, and you want to know it's the total cost, because I got to save up to be able to make this thing. Before I can even buy the fabric, I got to make the money to buy the fabric. So you might want to integrate not just the function 1 to find its surface area, but some other function. So if you want to integrate a function f of x, y, z over s, you just take the double integral over d of f ds. Okay? Good? So at each point, x, y, z, it just gives the function however much it costs or whatever at that point. So the way to do that is you take the double integral over d of, well, this same xs cross xt ds dt, that's a small s now, and then we want f, and it's f of x, y, z, which is f of x of s and t. So what you do is you just say for each point in the st plane, what x, y, z point does that take you to? This is then f of x, y, z, and this part is ds. So so that's what you would do. So to emphasize that this is just the same thing that we have been doing, like double integrals but over surfaces, let's try it over the xy plane and see that it comes out to the same calculation. So, for example, find the double integral over d of xy ds, where d is the unit disk in the xy plane. So I think this is something we've done before. This is a kind of cool looking surface. I will attempt to draw it. Looks something like that, and it sits over the circle. So it has 2 maxima in opposite places and 2 minima in opposite places, and it kind of looks like a Pringle sitting in space. So this is the edge of it, and it looks sort of like a Pringle, basically. This is f of x equals xy over the unit disk. I haven't drawn the surface, I've just drawn its edge. Okay, so method 1. Just use polar coordinates as before. So our usual method of computing this sort of thing. So we would say, okay, x is r cos theta, y is r sine theta. I want to integrate this thing over the unit disk. So I'm going to do double integral over d of xy dA is double integral from theta equals 0 to 2 pi and r equals 0 to 1. That gets me the whole unit disk. Okay, x times y. X is r cos theta, so that's r cos theta. Y is r sine theta, so r sine theta. And then dA, if I'm in polar coordinates, is r dr d theta. So times r dr d theta. So here this part was our x, this part was our y, and this part was our dA. So I'm not going to integrate this, but I think we've actually done it before. And actually, I've drawn this. The unit disk is actually here in the middle, and it comes out to 0, because the amounts above the xy plane cancel out the amounts below the xy plane. OK, let's try this with method 2. Parameterize the surface. And use surface area formula. So here, the surface, I don't mean that surface there. I mean this xy plane. So this unit disk in the xy plane, that's our surface. And at each point of our surface, our unit disk, we have a function value, which is x times y. So let's have x of r comma theta again. That just is going to parameterize our surface. It's just r cos theta, r sine theta for theta between 0 and 2 pi, and r between 0 and 1. That should give us the whole unit disk over which we want to integrate our function. So now we need xr and x theta. Let's compute them. xr is, oh yeah, and since this is in 3 dimensions, I'll actually put a z component on here as 0. So, because surfaces are generally in 3-dimensional space. So the derivative with respect to r is cos theta sine theta 0, and the derivative with respect to theta is negative r sine theta r cos theta 0. Now I need the cross product, the magnitude of the cross product. So the cross product of xr cross x theta is the magnitude of the cross product of these things. So I, j, k, cos theta, sine theta, 0, negative r sine theta, r cos theta, 0. And if you do this, this one is 0, the next one is 0, and the last one is just r. So it's the magnitude of r, which is r. OK. So now we're ready to use the surface area equation. So surface area is the double integral over the domain that you're interested in of the magnitude of xr cross x theta dr d theta. So for us, that's theta going from 0 to 2 pi, and r going from 0 to 1. I forgot my function. That's if I want the surface area. So the scalar surface integral is f of x of r theta times the magnitude of xr cross x theta dr d theta. OK, now let's do that. So that's f of x of r theta is r cos theta r sine theta 0 times the magnitude of this thing, which was r, times dr d theta. And so that's the same as the integral from 0 to 2 pi. R goes from 0 to 1. F of r cos theta, well, f is just x times y. So this is r cos theta times r sine theta times r dr d theta. So it came out exactly the same, and this r really is just a Jacobian expansion factor in the plane. The difference now is that we can integrate over things and use this Jacobian expansion factor when we're not in the plane, so over surfaces as well. Yeah. All right, thanks everyone.